Good morning, everyone. Welcome to the plenary session. CEDAR Distinguished Lecture, Modeling, Specifying, and Forecasting of Space Weather, which will be given by Professor Bob Shunk. It will be introduced by Professor Rob Hillis. The distinguished CEDAR lecture was instituted in 2009 to recognize individuals within the CEDAR community that have made sustained contributions to this within CEDAR. The Distinguished Award refers to a long-term sustainable work over a period greater than 10 years that has helped shape the CEDAR program through research and service. The recipient of the award presented an invited plenary lecture at the CEDAR workshop in June, which is happening today. I think I may have a couple of technical problems, so my announcements at the beginning might not have been heard about the Zoom links, and also that we'll be using a Slido to ask questions. I'm sorry about that. So with that, I will let Professor Rob Hillis introduce Professor Bob Shunk. Rob?
Thanks, Julio. Good morning, everyone. It's really a great pleasure for me to introduce this year's CEDAR Distinguished Lecturer. Bob Shunk has been at the forefront of ionospheric modeling for, well, let's just say a long time. He's well known for thorough treatments of important problems and for his candor in evaluating and interpreting the results. His book, Ionosphere, is a rather complete reference that many of us in this meeting, I think, will have consulted just to retrieve the principles governing the behavior of planetary ionospheres. But quite apart from providing this invaluable reference, Bob has also directed our attention to a number of fundamental ionospheric phenomena that are the foundations of our research today. His work on modeling the response of high latitude ionosphere to convection, for example, revealed features such as the tongue of ionization, the mid-latitude trough that we're still working on today. That same model showed the impact of ionospheric flows on frictional heating and ionospheric chemistry that are incorporated in models. And during that same time, Bob pointed out that the temperature in the high latitude ionosphere is critically dependent on the magnetospheric heat flux. This is a parameter that we're still trying to measure and calculate today. He was among the first to investigate the effects of photoelectron heating and temperature anisotropies on the outflows of H+ and O+ at high latitudes into the outer plasmasphere. And that work is now incorporated into models of ionosphere-magnetosphere coupling. But during his work, Bob's also been a critical evaluator of his work. He was the first to acknowledge the limitations of models that were poorly constrained by the lack of observations. And it was this appreciation of these limitations, I think, that led him to embark on the first data assimilation approaches to specifying the global ionosphere. Many of you may have heard of the GAME model that led the way to many more assimilation models that are being developed today. My objective here is not to make a full long list of Bob's accomplishments, but rather just to demonstrate that the breadth of work that includes the important problems that he's worked on, the results of which have a sustained impact on our field. And what this means is that Bob is someone who's worth listening to. You can learn a lot just by extracting a little from what he has to say. And it's for these reasons that I'm really grateful to be here and for the opportunity to introduce this year's CEDAR Distinguished Lecturer, Professor Bob Shunk. So Bob.
I am pleased and honored to present the 2020 CEDAR Distinguished Lecture. Clearly, I'm going to be talking about modeling, specifying, and forecasting space weather. But this is a very broad topic, and hence I will mainly discuss the work that I have been involved in during my 50-year Korea. In addition, the emphasis of my talk will be on the ionosphere thermosphere system. Attached is the outline of what I'm going to cover. First, I'll talk about what is space weather. Then I'll present some physics-based ionosphere and thermosphere models. This is followed by upper atmosphere ionosphere weather models. After that, I'll discuss multi-model ensemble prediction system. And then finally, I'll discuss averaging of data assimilation models. Now, I'm only going to give the big picture, an overview of what we have accomplished during my 50-year career. And after that, what I'll do is I'll provide backup slides with some specific references that will be very helpful. The first topic is space weather. What are the causes of space weather? Well, one of the main causes of space weather is solar weather. There are changes in the solar wind, there are solar flares, and there are coronal mass ejections. And in addition, you have plasma instabilities in the ionosphere and waves propagating up from the lower atmosphere. Sunspots are dark regions on the sun. They are located in the sun's lower atmosphere and are a result of stormy localized magnetic fields. The stormy magnetic fields choke the flow of energy from below, and hence sunspots are cooler than the surrounding area. Cooler regions emit less electromagnetic radiation and therefore are dark. Sunspots exhibit an 11-year solar cycle. High sunspot numbers mean the sun is very active, and this leads to intense space weather. From about 1645 to 1715, there was very little solar activity, and this period is known as the Maunder minimum. This period coincides with a very cold period on Earth known as the Little Ice Age. However, it is not clear if the low solar activity was the cause of the Little Ice Age. A solar flare is a sudden explosion of intense electromagnetic radiation from the sun's surface. Solar flares can produce enhanced densities in the ionospheric T region. They can also interfere with radio frequency communications and power line transmissions on Earth. Here's an example of a coronal mass ejection. It's a major explosion in the upper atmosphere of the sun, and as you can see during a coronal mass ejection, speeds can approach 2 million miles per hour. The mass can be 220 billion pounds, but the explosion power, if you like, is equivalent to 1 billion hydrogen bombs. So when a coronal mass ejection is pointed at the Earth and it hits the Earth, it'll have a major effect on ionosphere thermosphere weather. I hope all of you recognize this planet, but we want to go over some numbers in connection with going from the sun to the Earth. Earth is located at 150 million kilometers from the sun. Light takes about 500 seconds to reach Earth from the sun. The solar wind takes 2 to 3 days to reach Earth. And at Earth, the solar wind speed varies from approximately 200 to 900 kilometers per second, depending on conditions. The density of the solar wind at Earth varies from approximately 1 to 80 per cubic centimeter, and the temperature of the solar wind at Earth is 100,000 Kelvin in general. Here is an example of the effect that the sun's weather has on the ionosphere. The left diagram shows an auroral display as photographed from the ground. The right diagram is a snapshot of the auroral oval. The important thing to notice is the structure. There's a lot of intensity in this region here, but then there's none here. So this structure and the intensity difference is very important in describing space weather and ionosphere weather. Now, in addition to the structure and the precipitation, the convection electric fields, the horizontal and field line currents, they will also be significantly affected and have structure in them. Likewise, the ionosphere thermosphere system itself will be structured because of these variations in structure in the precipitation. And that's what we want to model, and that's what we like to specify. Here is a snapshot of the auroral oval during a 1-hour period. So these snapshots are roughly 10 to 12 minutes apart. To note that even in a 10 or 12 minute period, look at how the precipitation changes, the structure that occurs, and here there's very little precipitation except in one domain. Likewise, I indicated before, when you have this kind of structure in the precipitation, you're going to have the same structure in the convection electric fields, horizontal and field line currents, and in the ionosphere thermosphere system. And that is going to be difficult to model. But nonetheless, because of all this structure, you're going to get a number of ionosphere thermosphere features. Some of these include traveling convection vortices, sun-aligned and auroral arcs, propagating plasma patches and atmospheric holes, supersonic neutral winds, storm-enhanced densities, and spread F and equatorial plasma bubbles. As I noted in the previous slide, there are a wide range of weather features. I would now like to show some examples. I will show 3 weather features at high latitudes, 1 at mid latitudes, and 1 at low latitudes. The first one at high latitudes is the tongue of ionization. The tongue of ionization forms in a winter polar region when the interplanetary magnetic field turns southward. It forms in sunlight near the cusp. Anti-sunward plasma convection extends the high-density plasma across the dark polar cap, forming the tongue. The density of the tongue can be more than a factor 2 higher than the background plasma density. The second example of a space weather feature is propagating plasma patches. Like the tongue of ionization, the propagating plasma patches appear in a winter polar region when the interplanetary magnetic field turns southward. They form in sunlight equatorward of the dayside auroral oval. Patches can be either circular or cigar-shaped. The patch density can be up to a factor of 100 above background plasma densities. The patches drift in an anti-sunward direction with the background plasma. The figure on the left shows cigar-shaped plasma patches drifting in an anti-sunward direction across Greenland. The dimensions of these cigar-shaped plasma patches are 200 by 1,000 kilometers. The velocity of these patches is about 730 meters per second. This figure shows the third example of space weather at high latitudes. Shown are plasma drift velocities in the high latitude F region and a magnetic latitude, magnetic local time reference frame. The data were obtained with the ion drift meter on the Dynamics Explorer 2 satellite. The convection pattern appears to be turbulent. The ion drift velocities were measured during a crossing of the northern polar region when the IMF was northward. The traversal of the polar region took only 12 minutes, and therefore the highly structured drift velocities probably represent spatial structure in the convection pattern and not time variations. A careful examination of the figure indicates that there were 9 reversals of the flow direction. Therefore, this case corresponds to extreme space weather. This slide shows a comparison of weather features in the lower atmosphere, the troposphere. Here you have a snowstorm to the east of Utah, and we have another storm to the east of the United States. That's in the lower atmosphere, the troposphere. In the ionosphere and upper atmosphere, you have what's known as a storm-enhanced density. It's a ridge of high plasma density, and the density in the plasma ridge could be a factor 2 or more compared to the background plasma density. And this feature extends from below Florida up to Canada. And that's a nice comparison to show that you get storm features in the lower atmosphere and indeed in the ionosphere. Plasma instabilities in the F region can lead to spread F irregularities. In the equatorial region, spread F can lead to plasma bubbles at night. Plasma bubbles are vertically elongated wedges of depleted plasma that drift upward from beneath the bottom CEDAR layer to altitudes as high as 1,500 kilometers. A depleted wedge extends north-south along the B field, and it also extends east-west by up to several thousand kilometers. Basically, the bubble wedges look like upside-down watermelon slices. The east-west distance between separate bubble wedges ranges from tens to hundreds of kilometers. When bubbles form, their upward speed generally varies from 100 to 500 meters per second. However, fast bubbles can drift upward with a speed as high as 5 kilometers per second. The plasma density in the bubble can be up to 2 orders of magnitude lower than that in the surrounding medium. The next topic to be discussed is physics-based ionosphere and thermosphere models. During my 50-year academic career, I've been involved in the development of 5 global physics-based models of the ionosphere and thermosphere. The first model that we developed was the time-dependent ionosphere model, the TDIM. It's a global physics-based ionosphere model coupled to a global empirical thermosphere model, the EMPSIS atmospheric model. At high latitudes, you have to specify the convection electric field and aurora precipitation patterns as a function of time. At equatorial latitudes, you have to specify the equatorial electric field. The second model I was involved in the development of is the ionospheric forecast model. Basically, the IFM is the same as the TDIM, but has been modified to run faster than real time. This is because it was the first operational model that we developed, and it had to run faster than real time. The third model that I was involved in the development of is the ionosphere plasmasphere model, the IPM. It's a global physics-based ionosphere plasmasphere model coupled to a global empirical thermosphere model. The fourth model, IPM Global. This is a global physics-based ionosphere plasmasphere model extended to include high latitudes. The ionosphere at high latitudes is similar to the TDIM, but it includes a polar wind outflow at the upper boundary. The fifth model, the global thermosphere model, this is a physics-based model coupled to either an empirical ionosphere, a physics-based ionosphere, or a data assimilation ionosphere model. In what follows, I'm going to take 3 of the models and go into a little bit more detail so you can see what the features are in the 3 models. The ionosphere plasmasphere model, the IPM, has the following characteristics. The altitude range is from 90 to 30,000 kilometers. The altitude, latitude, and longitude grids can be set by the user. 6 ion species are included: NO+, O2+, N2+, O+, H+, and He+. A realistic magnetic field is used, the IGRF, the International Geomagnetic Reference Field. Some of the physical processes included in the IPM are field-aligned diffusion, cross-field electrodynamic drifts, thermospheric winds, neutral composition changes, energy-dependent chemical reactions, and ion production due to solar UV and EUV radiation, aurora precipitation, and starlight. Actually, the production due to starlight is important in the E region at night. Another model that is important for both our research efforts and our data assimilation efforts is IPM Global. This model is composed of an ionosphere plasmasphere model, the IPM, that covers low and mid latitudes, and an ionosphere polar wind model that covers high latitudes. The altitude range at mid-low latitudes is from 90 to 30,000 kilometers. At high latitudes, the altitude range is from 90 to 10,000 kilometers. As with the IPM, the altitude, latitude, and longitude grids can be set by the user. The model produces a fully global distribution. It contains the same 6 ions that were contained in the IPM. It also outputs 3D time-dependent distributions for the electron ion temperatures, and it outputs the drifts, plasma drifts both along and perpendicular to the geomagnetic field. Now, what is important is, as the high latitude regions expands and contracts due to geomagnetic storms, the B field lines open and close accordingly. So it's all self-consistent with regard to expansion and contraction of the ionosphere, plasmasphere, polar wind system. Another model that is very important for our research and data assimilation efforts is the Global Thermosphere model, GTM ionosphere. The altitude ranges from 40 to 800 kilometers. The altitude, latitude, and longitude grids can be set by the user. The neutrals that are produced, global distributions of the neutrals, N2, O2, and O. Non-hydrostatic and nonlinear flows can be described. We can describe with the model planetary, tidal, gravity, and sound waves. The model properly takes account of subsonic, transonic, and supersonic winds. It can also take account of wave breaking in the lower thermosphere. And an important issue, and I mentioned it earlier, is this global thermosphere model can be coupled to a global empirical, physics-based, or data assimilation ionosphere. Now, in one of the examples that we ran a period, we had the GTM ionosphere simulation. It included an equatorward propagating traveling atmospheric disturbance interacting with an upward propagating gravity wave from the lower atmosphere. And the interactions are described can be seen in this figure. The next topic to be covered is upper atmosphere ionosphere weather models. I should point out this is the global assimilation of ionospheric measurements I'm talking about, GAME. I should point out there were 7 core members for most of the GAME work, but now we're just down to 3 members. I should point out that Lutke Shearless, he's the common filter expert. He's the lead programmer for GAME. He works on data assimilation problems and anything connected with quality issues. His effort is very, very, very significant, and it is a continuing effort. It never stops. Larry Gardner, his work involves acquiring the data and checking data quality, improving and expanding the physics-based models, helping Lutke with data assimilation, and maintaining our computer system. And their part is definitely critical to the success of the program and into the future. This slide shows the 7 core GAME members. Starting on the left, we have Li Ju, Jan Soike, Lutke Shearless, Don Thompson, myself, and then on the upper right, Vince Eccles, and on the lower right, Larry Gardner. Now it should be noted that all 7 members were lead authors on important GAME papers. The backup slides provide papers published by the 7 core members, and that'll show which ones are important and which one they provided the main information for. Here are the 3 main USU GAME models. The Gauss-Markov model was an operational Air Force model from 2006 to 2020. The full physics model became an operational Air Force model in 2020. The third model is the Ensemble Common Filter for High Latitude Ionosphere Dynamics and Electrodynamics. That model is currently just a science model, it's not an operational model. In what follows, I will give an overview of the GAME Gauss-Markov and GAME full physics models. Over the years, we have conducted many data assimilation runs, and now both the GAME GM and GAME full physics models can assimilate multiple data types. The data are assimilated exactly as they are measured. We have assimilated bottom side electron density profiles from digisons, approximately 200. We've assimilated slant TEC from more than 1,000 ground-based GPS receivers. We've assimilated electron densities along satellite tracks, in particular the 4 DMSP satellites. We've assimilated integrated UV emissions from 4 instruments, LORAS, SULI, SUSI, and TIP. We have also assimilated occultation data from 5 satellites, CHAMP, IOX, SAC-C, COSMIC, and CNOPS. And again, I want to remind you that the data assimilated were at low and mid latitudes. This slide provides a brief description of the GAME-GM model. The ionospheric forecast model is the global physics-based model for the background ionosphere. This model covers 90 to 1400 kilometers in altitude. The data assimilation cadence is 15 minutes. The model covers the E region, NO+, N2+, O2+, and the F layer and topside, O+, and H+, and the electron ion temperatures. However, only the electron density is used by the GM model. The common filter solves for deviations from the background electron density. GAME-GM does not provide information about ionospheric drivers. By that I mean the electric fields, neutral winds, etc. In 2009, we created the USU Space Weather Center, and we started to run the GAME-GM model 24 hours a day, 7 days a week to provide continuous specifications of the ionosphere. This figure is a snapshot of a global run. 357 global TEC stations were used in the real-time run at the Space Weather Center. Approximately 10,000 slant TEC measurements were assimilated every 15 minutes. The left panel shows the vertical TEC specification, and the right panel shows the corresponding data. Note that for the right panel, the slant TE data were converted to the vertical TEC so that there can be a one-to-one comparison between the left and right panels. Also note that red corresponds to high TEC and blue to low TEC. In addition to the global GAME-GM run, we also ran a high-resolution regional GAME-GM run in real time. For this regional GAME-GM run, about 10,000 slant TEC measurements were assimilated every 15 minutes. The left panel shows a snapshot of the vertical TEC specification, and the right panel shows the corresponding data. As in the previous figure, red is for high TEC and blue is for low TEC. This slide provides a brief description of gameful physics. It is an ensemble common filter. The background physics-based model is the ionosphere plasmasphere model. At every time step, 24 to 30 IPM simulations are launched, each one with different drivers, different electric field, neutral wind, and neutral composition patterns. The assimilated data determine which of the 24 to 30 IPM runs is the best, and this process is repeated at every time step until the data, model, and drivers are in agreement. Gameful physics can assimilate 5 different data sources, as shown in the previous slide. The altitude, latitude, and longitude grids can be set by the user. The output of the gameful physics is ionospheric specifications, forecasts, and drivers. After the gameful physics model was ready for continuous real-time runs, it was installed at the USU Space Weather Center. This figure shows a snapshot of a gameful physics global run. Approximately 10,000 slant TEC measurements were assimilated every 15 minutes. In addition, bottom-side electron density profiles were also assimilated from 40 to 50 Ionoson/Digison stations. The left panel shows a snapshot of the gameful physics specification, in this case vertical TEC, and the right panel shows the corresponding data. The gameful physics model can also be run in a regional mode. Shown here is a snapshot of a gameful physics reconstruction for the US at 17 UT, day 82, 2004. The left panel shows the gameful physics measurements, vertical TEC. The middle panel shows the TEC reconstruction, vertical TEC. And the right panel shows the deduced meridional neutral wind at 300 kilometers in meters per second. We are proud of the fact that the game data simulation models have been or are currently running at the Air Force Weather Agency, now called 557 Weather Wing, Northrop Grumman, the Air Force Research Laboratory, the Naval Research Laboratory, the USU Space Weather Center, and the Community Coordinated Modeling Center. Scientists at JPL and USC have been working on data assimilation as long as we have. At some point, we decided to work together, and we created the multi-model Ensemble prediction system MEPS so that we can conduct ensemble modeling with data assimilation models. The current MEPS team members from JPL are Xiaoxing Pei, Tony Minucci, and Attila Kamjafi. The scientists from the University of Southern California are Chengming Wang and Gary Rosen. This slide shows the MEPS data assimilation models at our disposal. We had GAME BL, band limited, mid and low latitudes, GAME GM, Gauss-Markov, mid and low latitudes, GAME 4D VAR, mid and low latitudes with drivers, GAME full physics, mid and low latitudes with drivers. We have the mid-low electro data assimilation model, it's the Ionosphere with drivers. The ID-EDDA, it's high latitude with drivers. Global Thermosphere model DA, it's for the global thermosphere, and a new model, TWAM, Thermospheric Wind Assimilation Model. These models display global, regional, and nested grid capabilities that can be used for science, specifications, and forecasts. Further details about them can be obtained from the references given as backup slides. Meteorologists have shown that the best models for specifications and forecasts are physics-based data assimilation models. They have also shown that multi-model ensemble forecasts are very useful. The figure shows a multi-model ensemble forecast for Hurricane Rita. At the beginning of the MEPS program, we listed some initial tasks that we wanted to pursue. The first step is to select a storm period that we could model. Next, we wanted to select the MEPS models and data. After that, we want to conduct MEPS ensemble model runs. With the model runs, we wanted to then study the effect of different data types on the model runs. After that, we wanted to compare MEPS reconstructions. Finally, we wanted to study the usefulness of ensemble averaging in the ionosphere. The storm period selected for our study was 16 to 17 March 2013. The first day was quiet with a KP of about 1 to 2. The second day was a storm day with a KP of about 6. The models selected for this study are the 4 GAME models. All of them cover mid and low latitudes. We have the GAME band limited, the GAME Gauss-Markov, the GAME 4D VAR, and the GAME full physics. 2 of them calculate self-consistent drivers. The data that we're going to use in this study include ground-based GPS TEC, satellite-to-satellite occultation data, which yields the electron density at 800 kilometers, bottom-side electron density profiles using ionosons and digisons, and UV emissions, both 911 angstrom and 1356 angstrom, and emissions come from both the limb and disk. This figure shows the global data distribution. The white dots show the locations of 530 ground GPS receivers. The black dots show the locations of 80 ionosons and digisons. The purple dots show the cosmic derived electron densities at 800 kilometers. and the background is the game GM reconstruction for the quiet day at 21 UT. The goal here is to study the effect of different data types on the game models. So first we run all 4 game models with TEC data from 530 ground GPS receivers. After that we run all 4 game models again with data from 530 ground GPS receivers and cosmic occultation data. Then we do another run of all 4 game models with 530 ground GPS receiver data, occultation data, and data from 80 digisons. The goal is to see the difference in the model results and to see how the different models handle the same data type. This is the first step. We want to run the 4 data simulation models with just TEC data from 500 ground GPS stations. Here is the NMF2 comparison for the storm day at 2100 UT. Red corresponds to high NMF2 values and blue to low. If you look at the left column, you have the game 4D VAR at the top left, and beneath it you have the game band limited. For the middle column, you have the game full physics. Below that, you have the game Gauss-Markov. On the bottom at the right is the Ionosphere-Plasmasphere model, which is the physics-based model behind the game full physics. Now, clearly at looking at these results, there are similarities, but there are also important differences. Differences in magnitude of the equatorial anomaly are clearly evident. Some differences in longitude and the width of the equatorial anomaly are evident. The 4 models show enhanced NMF2 in the southern hemisphere beyond 30 degrees latitude. And again, I indicated that we only present the IFM to give you an idea of what a physics-based model would look like. This slide shows the HMF2 comparison for the storm day at 2100 UT. Again, red corresponds to high HMF2 values and blue to low HMF2 values. The format of the figure is the same. In the upper left, you got the game 4D VAR. Below that, you got the game band limited. In the middle column, you got game full physics at the top and game Gauss-Markov under it. And then the IPM prediction is given in the lower right. Again, there are many similarities, but there are also a couple of important differences. The equatorial region at 0 degrees and at 120 degrees longitude has significant differences. And at middle latitudes in the southern hemisphere there are significant differences. Now we want to run the 4 data simulation models with TEC data from 530 ground GPS receivers and satellite-to-satellite occultation data, which corresponds to the electron density at 800 kilometers. This slide shows a comparison of the 4 game reconstructions. This is a case where GPS and occultation data were assimilated. As with the previous slides, the results are shown versus geographic latitude and longitude. Red corresponds to high parameter values and blue to low values. There are 3 columns. These columns correspond to TEC, NMF2, and HMF2. The rows correspond to game Gauss-Markov, game full physics, game 4D VAR, and game band limited. Including the densities at 800 kilometers help to improve the reconstructions over the oceans. However, the differences noted for the GPS TEC data case alone are still relevant. As it turns out, 2 of the 4 game models were not able to assimilate the Ionosphere digison data. Therefore, I will only show the effect of the 3 data types on the game full physics model. This slide shows the results for the game full physics model at 21 UT on a storm day. The top row corresponds to GPS data only being assimilated. The middle row shows GPS and occultation data assimilation, and the bottom row shows GPS, occultation, and SAO data assimilation. The first column shows vertical TEC. The middle column shows NMF2, the peak electron density, and the right column shows HMF2, the peak height of the F layer. Red corresponds to high values, and blue corresponds to low values. A careful examination indicates that there is a difference, and we will look at that in a little bit more detail. This slide provides a more quantitative view of the effect of the different data types on the reconstruction. The format of the slide is similar to the previous slide. In fact, the top row is identical to the previous slide. The top row shows vertical TEC, NMF2, and HMF2. This row corresponds to the gameful physics reconstruction with GPS TEC data only. The middle row shows the change due to adding occultation data. The bottom row shows the change due to adding occultation and Digison data. Note that additional data affects the reconstruction at places away from the data locations. The data assimilation reconstructions are very similar, but there are important differences. The fact that the reconstructions are not exactly the same is not surprising, because the data assimilation models are based on different background physics-based models, different assimilation techniques, different spatial and temporal resolutions, different deduced electrodynamics drifts, different deduced neutral winds, and O to N2 ratios. Eventually, our goal is a systematic study to elucidate causes of the differences. The question is, will you get a better specification if you average the output obtained from the separate data assimilation models? Larry Gardner is the lead team member pursuing this issue. The period we're covering is March 12 to 19, 2013. It's the same storm period that we were considering in previous slides. Now, I should point out, in general, an ensemble of models can consist of empirical, physics-based, and data assimilation models. For this study, we're going to pick 5 data assimilation models and 1 physics-based model. Of course, it covers mid and low latitudes like in the previous slides. We're going to cover GPS and occultation data only. I should point out for this period, it's solar minimum, equinox, and as I said above, the storm period that we've been looking at all along is contained in this period. We're going to show results for a simple average of the models. In this case, you sum the models and divide by the number of models. And then we're going to look at a weighted average of the models. You sum the models weighted by the fit to the GPS data and then divided by the number of models. The models selected for this study are the 4 game models that we've been using all along and a new mid-low latitude electrodynamic data assimilation model. This model also provides drivers, and it is based on the physics-based ionospheric forecast model. And the 6th model is the ionospheric forecast model. And there'll be no data assimilation here, of course, it's just a physics-based model. For the simple average, the output from each of the 6 models was first put on a consistent grid. Then, at each grid point, the vertical TEC values were added and then divided by 6. This case included GPS TEC data and the occultation data, and by that I mean the densities at 800 kilometers. The figure is a snapshot at 2100 UT on the storm day. The figure shows the ensemble mean of the vertical TEC in the top right panel, the vertical TEC measurements in the bottom right panel, and the comparison of the data and the ensemble mean in the left panel. For perfect agreement, all of the ensemble mean TEC values would agree with the measurements, and that would fall on the 45-degree line. However, the ensemble mean shows well-defined equatorial ionization anomalies, and they are in good agreement with the measurements. The main conclusion of this study is that the ensemble mean at all times throughout the 7-day period was better than the individual data assimilation models. This figure shows the results for NMF2. As in the previous slide, the ensemble mean is shown in the top right panel. The NMF2 measurements from selected ionosons is shown in the bottom right panel, and the comparison of the ensemble mean and the data is shown in the left panel. The results are not as good as for the vertical TEC comparison between the ensemble mean and data. However, even for NMF2, a simple average of the 6 data assimilation models was better than any of the individual data assimilation models. This slide shows the results for HMF2. The layout of the figure is the same as in the 2 previous figures. With just GPS TEC and topside density data, all of the models had difficulty in capturing HMF2 because a given NMF2 could occur at different heights. Therefore, a simple average of the 6 models did not produce an improved result for HMF2. We also considered a case where a weighted average of the 6 ensemble members was used instead of a simple average. How Larry Gardner set up the weighted average is described in the Space Weather 2021 publication given in the reference list. For this specific case, the weighted average was slightly better than the simple average. However, a lot of additional work needs to be done before general conclusions can be drawn about how useful this technique is. Forecasting is very important, and we have to discuss that issue. We provide a 24-hour ionospheric forecast with our game operational models based on persistence of the IT drivers. So what do we mean by that? Well, persistence means you take the drivers from 24 hours ago and you use that to drive the IT model in the future. Now, I should point out that this persistence can be launched at any time. In other words, you can provide your forecast at whatever time you want. We also tried something else that is slightly different than persistence. We took the drivers from 24 hours ago and from 48 hours ago. We averaged them and used them in our forecast, our 24-hour forecast, and this seemed to work better. Now, in general, this forecast is more reliable during slowly varying magnetic activity. However, the forecast is reasonable at middle latitudes, somewhat reasonable at low latitudes, and totally unreasonable at high latitudes if magnetic activity changes appropriately in the future. And by appropriately, I mean significantly. A reliable 24-hour forecast for the ionosphere-thermosphere system requires reasonable forecasts for the IT drivers. And what do we mean by IT drivers? You have to have the convection electric fields, auroral precipitation, field-aligned and horizontal currents forecasted at high latitudes. The equatorial electric fields have to be forecasted properly at low latitudes, and upward propagating waves from the lower atmosphere have to be forecasted as well into the future. This is a very, very, very significant challenge for the next decade, and I don't know if we'll be able to achieve that. This is a summary of the MEPS system and how it can be used. Basically, MEPS is ensemble modeling with different data assimilation models. The data that's assimilated can be on multiple spatial and temporal scales in the different models. There's a wide range of ground and space-based data that's already been used, and it can be expanded upon in the future. This MEPS system can be an important tool for studying basic physics to find out what's happening if there's a new unknown phenomenon appear. You can combine different data sets into a coherent picture. So if you're an experimentalist and you have different measurements and you want to have a look at what's going on over a certain domain or over the globe, you can combine the different data sets into a coherent picture. You can also fill in regions where there are no data, and that's important. This really is a new approach for specifying and forecasting space weather, and I think it'll be valuable in the future when people start using it. Thank you.
Thank you very much, Bob. That was a really nice talk. Can we bring up the questions from Slido, please? So we have some questions from Slido. So first question from, what would you say is the best parameter to include in a simulation that would improve a specification of forecast? Bob?
You're muted, Bob.
Bob, if you hit the microphone button in Zoom, lower left, you should be able to unmute yourself.
Bob, can you hear us?
Bob, we can't hear you. You might have to hit the up or down arrow next to your microphone and pick a different source for your microphone.
Can you hear me now?
Yes, we can hear you now, Bob. And we can see you, we can hear you. Great, thank you.
I should point out that prior to this Zoom, I've only been on Zoom twice, and both times I had trouble.
No problem.
And even this is why I had a pre-recorded presentation.
So Bob, we can hear you fine. So why don't you take the first question there?
Okay.
So let me read the question again for you. What would you say is the best additional parameter to include in a simulation that would improve specification and forecast?
HMF2 would be invaluable.
Okay.
That would be very invaluable.
Okay. Okay, great. Thank you. There is a question from Julie Moses. I think it would be useful to have a slide of the years of investment in gain as an example of what it takes to produce operational space weather models. This is a great idea for a paper in space weather that would be very helpful to people, program offices involved in budgeting planning. I think that was more of a comment, I guess.
Yeah, we've been involved for more than 20 years.
Yeah, thank you, Bob. Okay, so there is a question from Dolores Nip. Are you able to compare with models outside of the MEPS family?
Yes, that's very easy to do. And in fact, the CCMC is doing some of that.
Okay, that's great to know, Bob. We have a lot of questions for you. There's another question from Suwei Pham. When different DA systems are carried out, the different ionosphere is produced. What are your validation metrics to evaluate which one is better? Do the results get better with more data?
The results definitely get better with more data. And typically we have independent data to verify which is the best.
Okay, thank you, Bob. We have one question. what is the difference between bubbles and irregularities in the equatorial ionosphere?
Okay. Irregularities could just be, like turbulence. Like turbulence. And then the bubbles is just the total depletion of plasma in a given domain.
Okay. Okay, thank you, Bob. I think we have time for maybe one or two more questions. So here there are a couple more, right? So this is a tremendous amount of work and many years. Let's see, I lost the question. Okay, this is a tremendous amount of work and many years of investment and development. Could you please tell if and how our research community can access the model output?
Yes, if you want to contact Lucas Shearless or Larry, you can get direct access for large data dumps. Don't forget, this is a lot of data.
Okay, all right. So maybe we can follow up this with by the channel in Slack. I think, can we bring up the questions up a little bit more, please? So we already answered the difference between bubbles and irregularities. There is, I think, one more question that we can entertain, Bob, from Osanjin Taiwood. Thank you for the awesome presentation. If I may ask, what method of assimilation would you advise the users of empirical models to employ for better accuracy? Also, I want to ask the best data source to be considered for data assimilation.
Well, GPS TEC data is the best because it's the most prevalent. But for the ionosphere, NMF2 and HMF2 really are critical.
Okay. All right, I guess we have two more questions. I think we might be able to answer this. Thank you. So this is a truly impressive amount of work on models and DA. Could you briefly highlight the reasons for having different models? Is this for ensemble forecast?
Yes. If you have different models, you can then, they're all going to come up with different results, no matter how good the individual data assimilation models.
Right, right. And then there is one final question. Are these data assemble simulation models running in real time?
Yes, they are. Some of them are running in real time. And the gameful physics is running in real time at USU.
Okay.
In real time at USU and at the Air Force Weather Agency.
Okay. Okay, Bob, thank you very much. That was an amazing lecture. It was really inspirational too to see your hard work. We commend you for that. Thank you so much for giving this talk today. So with that, we thank you virtually. And we're going to move on to the next talk. Thank you, Bob.
Thank you for having me.
So our next talk is a memorial talk, and it's going to be given by Professor Bella Feyer from Utah State University, and it's in remembering Stan Sazikin. Bella?
It's an honor to pay homage to the life and career of Stanislav Sazikin. Stan left us suddenly and unexpectedly in May 4th at the age of 49. He was known to be a distinguished computational physicist. For all who know him, he was one of the smartest people they have ever met, with a rigorous and penetrating mind. Stanislav was born in Kaliningrad, Russia. He earned a BS in physics and electrical engineering from the Moscow School of Physics and Technology in 1993 at the age of 21. The same year, he came to the US as an exchange student in the then USSR, USA, Bush-Gorbachev exchange program, and ended up in all places in Logan, Utah. In 1993, he started working in the physics department at Utah State University in rocket telemetry data. During 1993 and 1994, he was both a teaching and research assistant, and he earned a BS from Utah State in 1994 and started working my group in 1995. Since Stanislav had an engineering background as well, he first worked with Fred Biondi, John Merriweather, and I in the empirical modeling of equatorial and low latitude thermospheric winds measured by Fabry-Perot interferometers. For that work, in which he used a novel local two-dimensional regression analysis based on articles he found in the Journal of Econometrics and the Journal of the American Statistical Association, he earned an MS in 1996 from the Moscow Institute in Physics and Technology, and this degree was in space physics. As time went by at Utah, he received a BS at Utah State University in 1995. Following his MS at the Moscow Institute of Physics and Technology, he started working with me as a teaching, helping in my graduate math methods course, which he enjoyed very much. And then it became evident that he preferred to pursue mostly theoretical space science studies. So it was decided that he should go to Rice University to work with Dick Wolf on his theoretical space science studies. At Rice University, Stan reprogrammed the Rice convection model, a model of the Earth in a magnetosphere, under the direction of Dick Wolf and Bob Spiro. He used this model at Utah State University to study the effect of magnetospheric electric fields, which under disturbed conditions can penetrate all the way down to the equatorial ionosphere and cause significant perturbations on the plasma density and electrodynamics. He received his PhD from Utah State University in year 2000. And in the same year, he joined Rice University initially as a postdoc and later rose in the ranks to research associate professor. At Rice, he continued the work on the Rice convection model and was always the person everyone would go about learning in more detail about the Rice convection model and its uses. He also worked in collaboration with several other researchers on the study of how the magnetosphere generates very strong electric fields just equatorward of the auroral zone, causing what is called, among other things, subauroral polarization streams. This work was done using coupled ionosphere magnetospheric models, one in collaboration with Naomi Maruyama and the other one with Joe Huber. At Rice, Stanislav also worked on the magnetosphere of Saturn and on interpretation of data from the magnetospheric multiscale mission. Lately, among other projects, Stanislav's working on the response of equatorial electric fields and plasma density on two large geomagnetic storms using the Rice convection model, large databases of radar and other ground-based measurements, GPS-TC, and also plasma density measurements from the International Space Station. He was an active member of the scientific community. He served for years as member of the steering committee of GEM, the Geospace Environmental Modeling Program, and offers shared focus groups and meetings with humor and penetrating comments. At Rice, he played an important role in the development of the university policies for both teaching and research faculty. Stanislav was also heavily involved in Houston in youth soccer. Stan had an impressive background. He was interested in everything. The folks at Rice tells me that he was even giving advice of how to contest property tax assessments. He'll be sorely missed by his wife, Yankee, his 3 young children, and Andrew, Logan, and Victor, as well as by many members of the magnetospheric and ionospheric communities. His legacy, however, is going to live for a very, very long time. Thank you.
Thank you very much, Bela, for that memorial in honor of our colleague, Stan Sasinski. I didn't get a chance to meet him. I'm really sorry to hear about this loss. He died very young. I would like to take a moment actually of silence in memory of him. Thank you. Thank you. Bela, are there any initiatives from the family to establish a foundation or donation?
Well, it has. The Rice University has done that, you know, and actually very, very well. I mean, his colleagues at Rice, Dick Wolf was his, I should have mentioned Dick Wolf. Stanislav considered Dick Wolf his magnetospheric advisor, you know.
Oh,
yeah,
wow.
Yeah, he's, we work closely with Dick Wolf, and Stanislav has been doing lately a lot of work with me and his student Anastasia on these storm studies, which all came out from the initial interaction which all we had with Dick Wolf.
Thank you so much for sharing this tribute to him, Bela. If there is anything we can do to help his memory, please let us know how we can link.
Thank you.
Thank you. Thank you very much. So let's transition into our next speaker, who is Phil Chamberlain from the Laboratory for Atmospheric and Space Physics at the University of Colorado. And he's going to give a talk. The title of his talk is The Flare Irradiance Spectrum Model, version 2, FISM or FISM2, an improved model of the solar spectral irradiance are ultraviolet wavelengths. And you have questions, please use Slido to ask your questions. So with that, Phil, you can take it away. Thank you.
Okay, thank you, Julio. So thank you to the conveners for inviting me to come and give this talk on the newly released version of the Flare Irradiance Spectral Model, or FISM2, as we're calling it. It is a much improved model over those. I see a lot of colleagues on the line that have actually used FISM, the original version. And as Marty was pointing out yesterday, FISM was originally based on the C instrument Untitled, which Marty was talking about, the other Sabre, one of the other instruments on time, but time's now 20 years old. And we have a lot of new measurements that have come on board, as well as longer duration measurements that have covered now 20 years of the solar UV irradiance. So it was about time to put out another an update to this model to provide a significant improvement on it. So thank you again for allowing me to talk and share some of these advancements and how you can utilize this model. So this is just a quick outline of what I'll be talking about. Once again, I'm just going to introduce solar UV spectral radiance. This has been talked about a lot throughout this conference already, as one of the primary drivers and energy inputs into the Earth, especially the ionosphere and thermosphere. And I'm going to briefly present some of the measurements that we have made, because in any empirical model, it's only going to be as good as the measurements that make them. And then, once again, this community knows very well the space weather effects. Bob mentioned them some in his previous talk. That was a very good introduction. Some of the space weather effects that could be happening on all time scales of the ultraviolet radiance as a driver to dynamics in the ionosphere and thermosphere. And then the crux of the talk is getting into FISM2. What is FISM2? How does it fill the measurement gaps, and how accurately does it do that? And then I'm going to show you Lizard, which is the one-stop shop for any solar irradiance measurements that we have, or models such as FISM. And then what does the future have for us? So solar irradiance. Solar irradiance is really cool. With my involvement when I was at Goddard with SDO, SDO has an imager, an AI imager on board that produces these very beautiful images of the sun that you can see on the right. This one in the helium-2 30.4 nanometer emission line. And so what solar radiance does, though, is it takes all these beautiful fine features of the sun and just integrates over all of them. So it's kind of sun is the star. But what we can do then is get really high spectral resolution, as well as very large spectral range coverage, to accurately quantify the amount of energy the sun is giving off, and therefore the amount of energy that is an input into planetary ionosphere and thermosphere, as well as other things like lunar dust charging. So you see some examples of the solar radiance and the many features from a paper we published for a solar minimum reference spectrum in 2009, spanning many wavelengths and a lot of orders of magnitude in the actual irradiance variability. So zooming in on the ultraviolet wavelengths now, UV or ultraviolet wavelengths, we commonly break these down. There's an ISO standard right now that breaks these down into sort of the soft X-ray ultraviolet, or XUV, from 0.1 to 10 nanometers, the extreme ultraviolet from 10 to 120 nanometers, and the far ultraviolet from 121 to 200 nanometers. And what you see when you zoom in on this is you not only have the short wavelength high energy end of the blackbody continuum, but it ends up being dominated once you get to the EUV, partially in the FUV, definitely in the UV, and even more so in the XUV, by very strong free and free bound emission lines, as well as the bound emission lines. And so you have sources in here that come from all different temperatures, all different regions in the solar atmosphere. And because of that, they just don't all behave the same way. So when you get into sort of the empirical models that I do, you need lots of different proxies, or lots of different specifications for all the different individual lines, including some of them. So the coronal lines, the ones that you see in green, are mainly optically thin. There is some optical thickness to these emission lines and the soft X-rays as well. But these chromospheric and transition region emission lines in the blue and red are optically thick. So they behave very differently when you look at solar rotation timescales, as well as solar flares, that you need to take into account the optical thickness of these emission lines that are formed lower down in the solar atmosphere where it's more dense. And then you take this and you look at the solar cycle and the solar rotation variability. So you look at timescales of, sort of weeks on a solar rotation, days to weeks, solar rotation, how much this energy driver to the IT system can vary, as well as solar cycle. There's been a lot of people presenting on solar cycle, multi-decade changes in the solar EUV irradiance driver. I mean, you look at the amount of change, this very significant amount of change. It's shown in absolute values. The black is the solar minimum reference spectrum. The red line is for a very strong solar rotation, and the blue line is for over a solar cycle. And you see how much it can change. You see the percent change as a function of wavelength in the lower right. And you see it could change for solar rotation, solar cycles. Maybe it's only a 10% change in the FUV. There's some strong transition region emission lines in there that could change by maybe a factor of 2. But you look down at the very short wavelengths, the very high energy photons, and these can change by many orders of magnitude in these soft X-rays, factors of 1,000. So it's really important to accurately quantify this highly variable EUV, especially the XUV wavelength ranges. And the XUV is one thing that has drastically improved from going from the FISM 1 model that was released 15 years ago to this new version of FISM 2 that was released in December. And speaking to the CEDAR community, I think you guys are you all are the experts on this. I don't have to drill this in, but that lower left shows a plot I really like from Stan and Liang in their papers, showing where the energy is deposited as a function of wavelength in the atmosphere. It heats up the thermosphere, it creates the ionosphere, causing neutral density, electron density, neutral temperature changes on similar timescales as the solar driver, as seen by this plot from Judith Lean. And that in turn, even on terms of solar flares on seconds to minutes, this is a strong solar flare in this third plot by Eric Sutton that shows the Halloween storm in October of 2003, showing a large density change, neutral density change in the once again low latitude equatorial regions due to the high change in the energy input from solar flares. That is a very sudden change. And when you get density changes, you then look at, once again, when you talk about space weather, you really want to take it to how does this affect our technology? We've heard about radio blackouts that occur, but also satellite drag. There was a wonderful movie yesterday afternoon in one of the breakout sessions from a colleague at MIT that shows with these super constellations that are becoming more prominent and lots of satellites going up there, and with CubeSats going up there, it's getting really, really overly populated up there in space. And so conjunction analysis and accurately being able to predict the density at any given altitude that will lead into satellite drag is going to be very important going into the future. And in order to do that, you need to be able to specify the solar irradiance, solar UV radiance changes real time and at the frequency of seconds to minutes. You can't rely on a daily value if you want to do this, as you can see from the density changes due to the flare from Eric. So, and because all this energy is absorbed in the atmosphere, you can't observe it from the ground. You have to go up into space to be able to observe it. So you see a large suite of instruments that we have used over the past decade to 2 decades in order to accurately quantify the changes and the absolute irradiance of solar radiance over all time scales, from seconds to minutes due to solar flares, from days to weeks due to the solar rotation, sort of the lighthouse of beacon effect as the active region moves across the solar disk, and then over solar cycles. And that's another great improvement of FISM 2 is now we now have 20 years of measurements of accurately quantifying the solar irradiance. So now we have a solar cycle and a half to more accurately quantify and predict the solar EUV irradiance on solar cycle timescales. And now getting into FISM 2. FISM2, the flare radiance spectral model version 2 is now available. And I'm only going to briefly touch on some of the algorithms and some of the empirical modeling and some of the corrections that we do. But you see in that blue box there is highlighted, there's a publication that is now out that you could go in and find all the nitty gritty details of the model. A lot better job than I'm going to touch on here on the uncertainty calculation. And always please feel free to email me if you want to discuss this, if you want to work on how to implement FISM2 into your IAT model, data assimilation model, anything you want, please reach out to me. I'm very happy to help you get going on this and get this integrated. But as I said, the biggest improvement is the new measurement data set it's based on. These first 4 bullets are new measurements that cover a broad spectral range with sufficient spectral resolution of up to 1 angstrom spectral resolution and really good accuracy, as well as temporal cadence in order to quantify the variability due to solar flares and the space weather impact that those have. The bottom 2 are new proxies that are available, especially one I'm really excited about is the new GOES EUVS measurements that have now been publicly released as of a month ago. And this provides really good proxies of, as I was mentioning, the chromospheric and transition region emissions, these cooler emissions from the solar atmosphere that we haven't had previously on a high cadence. We've only had the soft X-ray measurements from XRS for the flare proxy, but now we have these really cool EUVS measurements that really show the impulsive phase of a solar flare. You see there's 2 sort of different phases on solar flares, the impulsive phase and the gradual phase. And so right now we're gonna hopefully be able to quantify the change due to this very quick, very first stage of the impulsive phase of a flare much better than we have before due to these excess measurements. And as I mentioned, all measurements are now 1 angstrom or better, which allows FISM2 to now be improved from its 1 nanometer bins that FISM1 was at to 1 angstrom bins. That really helps with the energy partition with the highly dynamic photoionization cross sections and feeding them in to really get that energy partition correct. And we've observed a lot more flares. SDOE has observed well over 1,000 flares, and Source Solstice has observed hundreds of flares at different times, at different wavelengths due to its instrument. And that's so much better than the FISM1 was based on 26 flares that happened to be observed by time C. So there's a much better data set to train the empirical model on, much more accurate, a lot more events, and spanning a lot larger time scale, as I said, now 10 years or 15 years. So this is kind of a quick example. Once again, please see all the details and there's a lot more examples, look at many different emission lines, different emission scales in the space weather paper. But this is just kind of an example. You see in the middle, the solar cycle. Marty mentioned this yesterday. Many folks have mentioned this. Bob mentioned it earlier today, the 11-year solar cycle on how the change in the UV irradiance happens. And basically, with an empirical model, you just want to train your larger data sets that cover a larger spectral range and train them to a set of proxies. Proxies are a subset, a handful of measurements that quantify the variability that you're trying to estimate, but they have much better temporal coverage, both higher cadence as well as over their temporal range over decades, if not multiple decades, in terms of XRS and Lyman alpha and magnesium 2 are some of the examples. But you just basically train it. They could be linear or power law relationships between the proxy, which is on the x-axis, and the actual measurement you're trying to model on the y-axis. So in this case, on the left, we're trying to do a solar cycle empirical model between the 17.1 nanometer proxy to the helium-2 304 measurement. And this is the solar cycle. So I've smoothed over 108 days to eliminate all the solar rotation variability and any solar flares that may be there, their daily average measurements. And so you see a really good sort of linear relationship between 304 and 171. And therefore, anytime now that we have the 171 measurement, we can now make an empirical model estimation of what the helium-2 304 solar cycle variation may be. And then on the bottom right, you see the same proxy and measurement, but this time I've subtracted off this 108-day smooth from the daily the daily average measurement, and you get the residual. So you get the solar rotation beating. As I said, this is the sort of days to week variability. That's the residual that's left over. So it once again will vary around 0. And you see that now anytime helium-2, 3, or 4 isn't available, we can now use this relationship to the 17.1 nanometer proxy to estimate the variability that is occurring. So this is just a simple linear relationship. And what you can see there then in the lower left is you see the actual measurements that were made from SDO-EVE. This is the version 7 data product that's soon to be released in blue, but we lost SDO-EVE MEGS A channel in mid 2014. So we no longer have that measurement of the helium-2 304 from SDO-EVE. But due to the relationships I just showed on the previous slide, we can now use a proxy such as the 171 or 17.1 nanometer emission line to extend this out. And so you see the FISM2 modeled there in black, because we still have 17.1 nanometer proxy over this time period. We're able to estimate what the measurement would have been would we have it. And I do want to point out that I also put in this relationship using F10.7 as a proxy, and you see it does not do a good job at solar minimum. You're off by about 10% at solar minimum, because F10.7 is not a good proxy during solar minimum time, and it's not a good proxy for solar rotation in general. So for those of you out there that still use F10.7 to drive any
Dr.
model,
Chamberlain?
Yes.
This is your 2-minute warning.
All right, thank you.
Yep.
And then so we see other wavelengths over there where FISM fills in the gap. And then when you get into solar flares, you have a lot of physics of solar flares between the impulsive phase in red and the black is the thermal gradual phase. And you have to model both of those as well. And so these are power laws. And so you use the GOES XRS for the gradual phase and the time derivative of the GOES XRS for the impulsive phase. Like I said, I want EXIS now. I have to incorporate these new cool measurements from EXIS, but I haven't done that yet. That's going to be FISM3. And you get these great power law relationships. What you see for optically thick emissions is that that flares in the center of the disk don't behave the same as flares on the limb of the disk when you use an optically thin proxy to model an optically thick emission line. So you have to also account for this center to limb variability of solar flares. Once again, all the details are in the paper, or please let me know. And then you're able to then simulate flares. You see the black line are SDO-EVE measurements, and the red line are the FISM2 measurements of solar flares, as well as breaking it down into the impulsive phase, green, and the gradual phase, purple components if you want to do that. But red is really the final product. And then you get the uncertainties, the increase during solar flares. And you see a lot of variability. I already showed this slide showing the amount of variability, the percent change by orders of magnitude in some of these wavelengths during solar flares. And so once again, we realize there's lots of data sets out there and models. So we have this Lizard data site set up. There's a one-stop shop that you could get all those measurements that I showed in the previous slide, time C, SDO-EVE, source solstice, MINX, but you can also get FISM. And you just type in FISM2 into this search bar and you come up with data products. And I do want to mention that I already have a data product that's being served here that is already binned into the stand bands and is at 5-minute cadence that hopefully will eliminate a step if you want to integrate FISM2 into your models such as WACM-X or time GCM. And I know I have a task right now that I'm trying to get and provide it in the EUVAC bins. So just in conclusion, there's large data set out there of measurements, but there's still gaps in those. And if you want to fill those gaps and you want to provide accurate solar EUV irradiance inputs into your model to fill these gaps, FISM2 is where to go. And F10.7 is not sufficient, especially on solar rotations timescales and especially during solar minimum times. I want to keep stressing F10.7. We should move beyond F10.7 as a community. And in the bottom left, there's a lot of future instruments that are coming along that will help improve the measurement accuracy on lots of timescales and a lot of these wavelengths, especially in the soft X-ray, that we want to take advantage of. So thank you very much.
Thank you very much, Phil, for that great talk. That was really great. So we're running out of time in the, but maybe we can have some questions from Slido. And I have one question actually. So you say F10.7 is not sufficient. We've been using that for a long time.
Yep.
So what would be the change? What would be the new version of that?
So, so one thing I'll present, I added in the FISM 2 slides tomorrow for a modeling session. But one thing we can do, I mean, the best thing to do is use the full spectral radiance model into the cross sections, into the full physics. But one thing you can also do is just sum up 0 to 100 nanometers or 0 to 190 nanometers and use that as a in-place proxy, or QEV 0 to 50 nanometers. And Lisa and Cole, who just published a paper, have proven that just doing that provides a much better proxy for an empirical TEC model that they have just published, that I encourage you to go look. And it's in slides in a breakout session tomorrow that I provide some examples of that. But that's a simple thing to do, is just integrate from 0 to 50.
Okay, thank you. Thank you so much. Can we bring maybe a question from Slido? Okay. Let's see. Great work, Phil. What is the latency of FISM2 and providing the beam values for EU VAC?
Yeah, so unfortunately, the latency is about 6 days right now. Because it's a huge, I would love, and I hate answering this question. It's a great question. I hate answering it, but it's unfortunately a funding and an effort issue. I would love to get the fund. It's a lot of effort to provide, as many on here know, to provide a real-time, redundant, or accurate space weather model that runs in real time. It can be done. It can be done for forecasting. I would love to do that. Unfortunately, I haven't been able to secure the funding. Personally, I've written some, I need to be better writing more compelling proposals. But I hope to, in the future, to provide a real-time as well as a forecast version of FISM. I have plenty of ideas how to do it, just not the time to do it.
Okay, Phil, I think we don't have time to answer. There are 2 more questions on Slido. We can pass them for CEDAR Slack, so we can follow up maybe with your answers from that channel.
Most definitely.
Want to thank you. This was a really great talk. Fantastic.
Thank you.
I want to thank, I want to thank all the speakers, and I also want to give my apologies for my technical problems at the beginning of the session. Things happen, sometimes. I want to remind everyone, please, that to check the Zoom links have been updated in the main CEDAR website. So please check the Zoom links for the workshops or the remaining workshops. We have a break now, supposed to have a 10-minute break, but running half of the time to that. So please enjoy the rest of the meetings, the rest of the workshop you want to participate. And with that, I will stop the plenary session. Thank you so much.